So, welcome to the 22nd lecture of surface engineering. Well, having first defined what is surface engineering, and but even before that, we started talking about various classification of engineering solids, the evolution of microstructure, the various defects associated with solids, and we classified various kinds of surface engineering techniques. But before that, we also classified different surface dependent properties of the physical, chemical, and structural properties or mechanical properties. And then we discussed at length about each of these properties separately. But now is the time when we actually should discuss specific surface engineering techniques. To begin with, we may broadly classify the entire gamut of surface engineering into two major groups, the conventional surface engineering, which are very age-old practices, very well established, and many of them are still very widely practiced because they are economical and they are easy to implement, and they have a large utility in various manufacturing practices. We also will discuss some of the advanced surface engineering techniques, which could be essentially thin film based or using direct energy beams and so on. So, to begin with the conventional practices, the very first technique we are going to discuss today is called short peening, or peening for that matter. In fact, if you just think of a hammer, so if this is the hammer, one portion of the hammer will have a flat head and the other portion will have a round head. So, this rounded portion is called the pin. So, the blunted or the rounded head of the hammer is called the peen. And when you hit any flat surface with this kind of a rounded head, so obviously it is going to create certain deformation, and that will be a diffuse deformation. When you deform, then you create a deformation zone underneath, and that particular zone, if it is a metallic material, is likely to create certain higher density of dislocations, and also because of the recovery process, there will be residual stress developed, which is compressive in nature. So, this is the principal theme of short peening, that you apply limited surface deformation and the material deforms only up to a very limited depth, but during the process of recovery, certain amount of state of stress is created, which is residual in nature. That means when you have removed the load, still that particular stress remains, and that stress incidentally is of compressive nature, which is beneficial for very many mechanical applications, or applications which actually subjected to various mechanical deformation. So, when we actually try to deform, there is always, if you look at the typical stress strain diagram, there will be initially an elastic region proportional and then followed by a plastic deformation region. So, we are essentially talking about this region which is beyond the yield stress. But this deformation zone, as I said, is very limited from the surface. So, if this is the bulk, we are talking about just, way less than millimeter, maybe only a few micrometer depth of deformed layer. So, this deformed layer is limited to what is known as subsurface region. The bulk may actually develop residual tensile stress, but the surface will develop residual compressive stress. So, what are the benefits? Why do we intend to do that? These kind of residual state of stress, which is compressive in nature, actually is useful, so that because it provides resistance to crack opening or propagation, it improves the fatigue life or reduces fatigue failure, it creates resistance to corrosion fatigue, stress corrosion, or cavitation erosion. So, all these surface damages are reduced, minimized, or in some cases even prevented if we can create such a state of stress which is compressive in nature. In certain manufacturing operations, for example, welding, and that too welding of cast iron, there is no post-weld treatment possible, and we all know that in any fusion welding process or fusion joining process, when the liquid solidifies, the state of stress on the surface is tensile in nature, which is not very conducive for creating or inducing greater fatigue strength. In other words, if there is a crack onto the surface under residual tensile stress, the crack can easily open. So if you have a crack here and if you have a residual tensile stress, then obviously this crack can very easily open, and we don't want this to happen. So we would always prefer to have a situation where the state of stress is working towards each other or compressive in nature. So for a welded zone, particularly at the root of the welded zone, if we can create such residual compressive stress by way of hitting with ultrafine spherical balls, then that is beneficial. It can be done on a flat surface, it can be done even on curved or surfaces with complex geometry. So there are three possible ways of introducing such residual compressive stress onto the surface. Typically the shot peening, where we use spherical shots; needle peening, where actually we use a cluster of needles, very fine ultrafine needles made from hardened steel; or we can do hammer peening. So this can be a single metal rod hitting onto the surface, and so this is wider. So this is the finest, and this also could be fairly fine, but this is the widest or the wider level of deformation done onto the surface. Now, for shot pinning using this impacting spherical shots, we actually can enhance the fatigue strength, as I mentioned, on typical engineering components like gear parts, the camshaft, clutch spring, coil spring, connecting rods, crankshafts, all kinds of rotating members, rock drills and so on, where fatigue is a standard way of failure. And if we can create a residual compressive stress onto the surface, then we defer, we actually in some cases even prevent such crack growth or fatigue failure. So it's a cold working process, obviously, because most of these are done at room temperature or certainly way below the crystallization temperature. So the deformation zone or the deformation effects are retained onto the sample. It imparts small indentation, just like when we use for hardness testing. When we press a hardened steel ball onto the surface, we create an indentation. In the same way, but the spherical objects that we are throwing are ultrafine, very small, so the indentation size is very, very small. And this indentation is done by so-called spherical objects called shots, and the effect is called peening, just like it is very similar to the peening with a hammer. So the forces that actually we apply for individual impact is actually compressive in nature. So there is a very small deformation zone, and so initially, let's say this is the object which is propelled onto the surface at some very high velocity. So when it impacts to the surface, we create certain deformation zone like here, and as we create deformation zone, we try to push the material downwards, and the reaction to that will be such that the material will try to come back. And when it tries to come back, the state of stress that we create onto the surface is compressive in nature. So we create residual compressive stress onto the surface. Now this is for a single impact. If we have multiple impacts of very small size balls, we are talking about 0.5 millimeter, so fairly small, 500 micrometer. And when we have multiple such impact events occurring onto the surface, so they are all essentially incident onto the surface, and when the first impact occurs, the second one actually need not come simultaneously at the same spot, but the second one comes after a time lag, and when it falls in another portion, there will be some overlap of plastic region. So if this is the plastic zone created by the first impact, the second impact, which will have certain overlapping region, will have this amount of overlapping zone. So in the process, the deformation that we create onto the surface will have more or less uniform depth, but also will have fairly homogeneous deformation structure onto the surface. So we end up getting a region onto the surface which will carry a compressive state of stress. Now, what are the various media that we can use for such impact making? We can use spheres made of hardened steel. We can use cut wires of steels of high aspect ratio. We can use glass beads which are very high elastic modulus. We can even use ceramic beads which can have even higher modulus. So, these are non-deformable substances, very high hardness, and most importantly rigid, and they don't deform. In fact, they do deform, and if they deform substantially, then we need to change the set of shots that we are using for shot peening. The diameter usually is very similar or the same throughout the media. Now, we control the intensity by applying certain empirical relationships, which is created through by using so-called the Allman strip. So, essentially you actually have a steel strip onto the surface, and then by way of hitting by these shots, the strip actually bends towards the impacting side, and by looking at the angle of bending, we actually can make an educated guess about the amount of compressive stress that we are creating, and accordingly we can actually manipulate the velocity and hence the momentum with which these shots are impacting the surface. So, when we actually allow such shots to hit the surface at very high speed, we actually can make use of this kind of a calibration using the Allman strip to control the speed and control the level of stress that we can generate onto the surface. So, there are very many advantages of using such an action. So, the first and foremost thing, or the principal thing, is that we are able to create such residual compressive stress onto the surface, and this goes on to prevent various types of corrosion, galling, fretting, or cracking type of a wear or abrasion. It can minimize or prevent hydrogen embrittlement. It also creates certain very small dents. Instead of pores, I would rather call them dents, and these dents actually could, so on the surface you create such little bit of waviness, the depth of which could be much less than tens of a micrometer, maybe a few micrometers, but these dents actually are good, so because they can reserve some amount of or contain some amount of lubricants which actually are useful for subsequent motion between the surfaces. Usually by way of this deformation, we actually create certain deformation texture, but the finished surface can easily be subjected to final finish or painting. Now, the benefit wise, the biggest benefit, for example, here we are describing the number of cycles, so essentially the state of stress or the maximum stress required for failure for a given number of cycles. So, the maximum number of cycles required for failure. So, this we know typically is the so-called endurance limit, and when we have the same material subjected to severe grinding operations, gentle grinding operations, and severe grinding followed by short peening operation, what we see is that at any given number of cycles, the endurance limit is always highest. So, the maximum endurance is created when we follow grinding with short peening. So, this kind of short peening operation, for example, is very useful on all rotating parts I already mentioned, and such kind of a big crankshaft we can introduce. Now, because of the large size, you cannot do any operations easily on this kind of a component, but you can bring in a gun and you can do short peening on this kind of a surface, curved surface, and create residual compressive stress, and that's how you can improve the fatigue strength. I have already explained that when the impact happens, you actually create a small indentation or so-called dimple, and there is a little curvature created, and this curvature, due to multiple subsequent shots from several other randomly falling objects, will essentially create a uniform depth of deformation and uniform area coverage throughout the surface. The biggest advantage, always we should remember, is the creation of this state of compressive stress onto the surface, where the forces are actually acting towards each other, and hence if at all there is any crack or discontinuity created, first this crack has to see a situation where the state of stress is reversed from compressive to tensile, and then only this crack can further open. So this is kind of a preventive measure created by the state of stress, which actually prevents any kind of crack growth, particularly under fatigue or such operations. So you can do mechanical short pinning, you can do dual pinning, where you can actually have pinning initially with a particular size followed by another size, maybe a smaller shot with lower intensity. So actually if this is the depth of the deformed zone, then actually the state of stress that you create can vary. So it actually, everything is negative, but the amplitude will be lower or higher along the depth. So as a result, you can have a graded state of stress toward the surface. Instead of mechanical impact, you can use a laser assisted shock wave, which can create such state of compressive stress on the surface. You can also do strain peening by using other kinds of impacting objects. So this is sort of an idea as to how small these shots are compared to the overall surface that we are trying to treat. So in this cartoon, you cannot make out the size difference, but imagine this is less than a millimeter, maybe 0.3, 0.4 millimeter. And this surface area can easily be a meter by meter or half a meter by half a meter. So obviously, you require a gun which actually will be throwing these projectiles, and the projection will be little divergent, but depending on this distance and the velocity with which they are coming, the size and the weight and the material of these shots, the state of the condition onto the surface, the angle of incidence, all these parameters will determine what will be the state of stress. Now, so this is, if this is the neutral plane and this is the tensile side and this is the compression side. So by way of introducing such short pinning, you actually always create a residual stress which is compressive in nature. And this actually can be fairly large. For example, the total at certain depth below the surface, you actually can have fairly large large magnitude of residual stress created. So there are actually various factors which influence the residual stress development onto the surface. The most important thing that we have to realize that if you are talking about a large surface area and each of the shot is only this small, then you actually need quite a bit of the entire operation should have a fair amount of overlapping. Otherwise, you cannot create a uniform state of stress throughout. And this kind of possibility is can be actually modeled through typically an Avrami equation, which is a function of the size and the velocity and also the speed at which they are covering the entire surface integration for the entire surface. So parameters that we need to actually take into account are the mass and the rate at which the mass is impacting the surface, the density, the radius of these shots, obviously the area that is spread under the deformed zone, and certainly the time for cumulative time for this entire process. Okay. So imagine, so this is the fatigue strength of a particular material against the UTS of that particular material. Now, when you compare different kinds of conditions, so this is the condition of the particular steel without without short pinning. This is with this is also without short pinning, but this is with definite amount of short pinning. So that means after the short pinning operation, what we see is that the fatigue strength of the material is uniformly increasing as the UTS of the material is going up, or in other words, at higher and higher level of UTS or higher level of hardness level, we actually see after short pinning that the fatigue strength of the material uniformly increases. So that certainly is very, very beneficial for all kinds of rotating components. In fact, for a given steel, which is carburized steel, now normally we haven't discussed as yet, but carburizing treatment followed by a certain surface thermal treatment develops predominantly martensitic microstructure. And when we develop martensitic microstructure, then we actually may expect that the state of stress onto the surface is residual compressive in nature. But what is shown here is that for a carburized steel, this is the neutral plane. So obviously this is in the compression zone. So the residual stress is compressive in nature, but when you actually follow the carburizing and heat treatment follow it up with short pinning, then the state of stress can be actually much higher in magnitude in the negative direction, meaning the magnitude of residual stress is much higher if you follow up carburizing with short pinning. So at higher and higher level of pinning velocity, you develop actually much higher residual stress. But what is even more important is that the state of stress actually is confined to very shallow depth from the surface. So you leave most of the bulk unaffected, only the near surface region is affected, which can be just about 100 micrometer or less. There are typical advantages. For example, this process, I told you at the very beginning that we consider short pinning to be one of the conventional practices, but it is being used for more than 100 years, but that's simply because the process is very simple and inexpensive and can be easily applied. You don't need a very high level of skill set for applying this short pinning. And it can be, the most important thing is it can be used on all kinds of metals, not just steel. For example, non-ferrous metals or cast iron or various kinds of metallic coatings and welded joints and so on and so forth. But usually confined to metals, because you do require certain deformation, plastic deformation, generation of dislocations, higher dislocation density, which is what will be responsible for creation of residual compressive stress. For example, if you're, on the other hand, if you're talking about silicate glass or nitrides or carbides or borides or boride coated components, it's very difficult to imagine that short pinning will create residual compressive stress onto the surface, because there's no surface deformation possible by way of impacting with this steel shots. But there are certain disadvantages always. For example, if you are talking about a large surface area, then to cover the entire surface area and make exactly uniform state of stress requires quite a bit of trial and various kinds of experimentation. And there will be always certain level of variations at submicron level. Also, we believe that we expect the shots should always remain geometrically spherical and maintain the same level of hardness. But these ones are supposed to be very rigid, but if you're dealing with steel shots, or even you can use carbide shots or some other ceramic materials, but they do get deformed after a while. So instead of complete spherical, if this becomes oblate or such kind of a non-spherical shape, then obviously the shot can hit either in a flat condition like this or in a perpendicular condition like this. So as a result, your entire Hertzian distribution of impact is going to be affected. So whatever you have calibrated, you may not derive the same effect. So in that case, we need to make sure that the shots should actually remain spherical. And just to ensure that, what you should do is, depending on the material that you are treating, beyond a certain period, you should change the shots time to time, or introduce fresh lot of shots. so we need certain changes at regular intervals. And also, if you have really very complex shape and geometry, now normally because the shot size is very small, as I said, much less than a millimeter, maybe less than even half a millimeter. So even at the root of a weld, you can expect shots to cover. But if you have really very complex shape and also crevices like this, then it's very difficult to go all the way down. So for example, if you are dealing with a ball bearing and the bearing is very complex where the root is very, very narrow and very deep below, then there will be difficulty in reaching up to the bottom of the root, bottom of the teeth. So again, here is a nice comparison that this is so this is basically the rotating bending stress that the member experiences, and this is the number of cycles. So when you have a carburized condition of steel, this is how the fatigue behavior is expressed. When you actually follow up carburizing with conventional shot pinning, then the situation is improved. So you have slightly higher endurance limit. But when you have carbonitriding followed by hard shot pinning, then the fatigue life is significantly improved. So it's not just the surface treatment alone, I mean the chemical treatment alone, which fetches the result, but combination of the surface chemistry change followed by this mechanical control deformation can actually give you much higher fatigue strength. And this actually is important for all kinds of metallic materials, particularly various types of steel. So here is a carburized steel on this particular alloy, and this is a spark gears. And so typically the number of cycles required for failure would be much more when you have high intensity shot pinning on the same material. So time to recapitulate. First of all, we have understood what is a peen, which is the rounded or the blunted head side of a hammer, and peening means as if you are hitting with such blunted heads. So when you hit, you deform up to a limited depth, and this kind of a deformation can create a certain level of accumulation of dislocation, creation and accumulation of dislocations, which in turn can create a residual compressive stress. So and that brings in certain beneficial effects as far as fatigue strength or several other mechanical properties are concerned. The mechanism is more or less same, no matter what kind of peening process we are doing, whether with shots or pin needles or with some other agencies, wires and so on. But so principal mechanism remains the same. The state of residual compressive stress is created because of the mechanism that I just explained, that you deform, you indent, the material flows, and the reaction to that is to bring the material pull in to the center. So you create a state of stress which will actually act towards each other. So this kind of a state of stress which acts towards each other is the compressive stress, and onto the surface, when we create that by way of this short pinning, we create higher or improve the fatigue strength. Usually metallic materials and alloys which actually are amenable to deformation, plastic deformation easily, they are the ones which are suitable for short pinning, and not the ultra hard or non-deformable rigid solids. For example, you don't do it for a semiconductor or a carbide or nitrided surface and so on. The process of short pinning is throwing of those hard objects onto the surface, plastic deformation, tendency to recover, and then creation of the state of stress, which is compressive in nature. And this is what we need to understand, that how it varies from material to material. So obviously you won't throw at the same velocity with the same mass or the same size of the shots to all kinds of metals. I mean, it cannot be a universal velocity, size, and type of materials that are used as shots for different kinds of materials to be shot pinned. what actually we learn, a final takeaway from this discussion so far, is that even though it is a conventional process, but shot peening is still a very widely practiced, economical, and very, very effective means of creating residual compressive stress on flat or curved surfaces, even with complex geometry, so that we are able to create residual compressive stress. And for all rotating members or members which actually experience cyclic stresses, this creates a higher fatigue life for the material. Thank you very much.